Alright, welcome back. We're working in Chapter 2 now. Chapter 2 is Congruence in Z and Modulo Arithmetic. Focusing on Section 2.1, Congruence and Congruence Classes. Definition. Let A, B, and N be integers, with N being greater than 0. Then, A is congruent to B modulo N, written in the form A and the three little lines, that's congruent. A is congruent to B mod N, little parentheses there. If A is congruent to B mod N, if N divides A minus B. So, and again, this is an equivalence equation here, but it is an equation. So writing this stuff up, writing it like 17 is congruent to 5 mod 6 is perfectly acceptable. That's symbolism we do allow here. So because it's an equation style. But now, why is this the case? Why is this true? Why is 17 congruent to 5 mod 6? Well, the definition of congruence modulo N, A is congruent to B mod N if N divides A minus B. Because 6 divides 17 minus 5. We'll double check it. Now 17 minus 5 is 12, and clearly 6 divides 12, so that's a winner. Next one, 4 is congruent to 25 mod 7. Why is that the case? Well, that's because 7, what you're modding out by, divides 4 minus 25. Now 4 minus 25 is negative 21, and clearly 7 divides negative 21. And the last one, 6 is congruent to negative 4 mod 5, and the reason for that is 5 divides 6 minus negative 4. Now, 6 minus a negative 4, that's 10, and clearly 5 divides 10. So, A is congruent to B mod N, provided that N divides A minus B. So not just N divides A or N divides B, which is what we did in Chapter 1. Now N divides the difference, A minus B. And remember, this is the notation that you write it. A is congruent to B mod N. Now, this congruence class has particular properties. And so we want to define some of these properties for you guys, because you have to have these three properties to have an equivalence class. The three properties are reflexive property, symmetric property, and transitive property. Now I'm going to use the standard tilde for congruence, whatever, because there's lots of different kind of congruences out there. So this is just a standard definition congruence. The reflexive property is, given any element, you're always congruent to yourself. A is congruent to A. The symmetric property says that if A is congruent to B, then B is congruent to A. If A is congruent to B, then automatically that forces B to be congruent to A. That's the symmetric property. And the famous transitive property. If A is congruent to B and B is congruent to C, then A is congruent to C. So, look at what theorem number 2.1 states. Let A and B be positive integers. Well, it's going to be let A be a positive integer. And for all A, B, C, and this is a little symbol, elements of Z means these guys are integers. A is a positive integer, and for A, B, and C being integers, we have this. Number 1, A is congruent to A mod N. 2, A is congruent to B mod N, then B is congruent to A mod N. And 3, if A is congruent to B mod N and B is congruent to C mod N, then A is congruent to C mod N. Now, if you look at this theorem, what they're really telling you is this. Given any positive integer A is congruent to A. No, actually, it's the N supposed to be positive. I have to go on that one. Let N be a positive integer. And for all A, B, and C in integers. See, this is what you're modding out by. You can only mod out by a positive integer. So A is congruent to A mod N. Now, what was the definition of A is congruent to A mod n? What's the definition of modulo n? This means n divides A minus A. Well, A minus A is 0, and clearly n, being a positive integer, divides 0. Everybody divides 0. This is a true statement. But A is congruent to itself means you have the reflexive property. Look at the next one. If means given. So if A is congruent to B mod n, so you're given A is congruent to B mod n, then you get for free B is congruent to A mod n. Reason for that? If you're given A is congruent to B mod n, that means by definition n divides A minus B. And if n divides A minus B, then n is going to divide -1 times A minus B. And -1 times A minus B is actually B minus A. So n divides B minus A, so you get for free, that's the definition of congruence modulo n. A is congruent to, B is congruent to A mod n. And the last one, so this is the symmetric property. This last one is the transitive property, obviously. If A is congruent to B mod n and B is congruent to C mod n, then A is congruent to C mod n. Let's talk about that for a second. If A is congruent to B mod n, remember, if means given. So you're given A is congruent to B mod n. That means n divides A minus B. You're also given that B is congruent to C mod n, which means by definition congruence modulo n divides B minus C. So I've got n dividing A minus B, and n divides B minus C. So I've got n dividing A minus B and n dividing B minus C. So if I add these two guys together, I'll get A minus B plus B minus C, which is A minus C. And if n divides two parts, then n is going to divide the sum and difference. So therefore, n divides A minus C, and therefore A is congruent to C mod n. There's the proof, literally, just with me talking you through it. But what this theorem is telling you is that you've got to have the reflexive, symmetric, and transitive property have a congruence class. We have congruence classes when it comes to modulo n. So let's take a look at this guy here. So this is Theorem 2.2. Theorem 2.2 states this. If A is congruent to B mod n and C is congruent to D mod n, then 1, A plus C is congruent to B plus D mod n, and 2, A times C is congruent to B times D mod n. So what we're saying in this theorem is not only do in the last theorem we have congruence classes, we actually are defining how to add these congruence classes and multiply these congruence classes. Now, I'm just about to post your second homework set. Your first homework set is going to be due a couple of days here, but your second homework set is going to basically make you prove this first part here. Given that A is congruent to B mod n and C is congruent to D mod n, you have to prove that A plus C is congruent to B plus D mod n. I'm going to prove part 2 for you on this one, okay? So, with that being said, let me prove to you part 2. Alright, so here goes my proof. Always start with the givens. You can do this on a scrap sheet of paper, but I'm going to actually write it up properly here. You were given that A is congruent to B mod n and C is congruent to D mod n. So since you're both modding out by the same thing, n, you can kind of put these two guys together. By definition of congruence, modulo n, what does it mean for A to be congruent to B mod n? This means that then n divides A minus B, and what does it mean for C to be congruent to D mod n? and n divides c minus d. But we got the divides part. Now here comes back to chapter 1 again. That's the definition of congruence modulo n. N divides a minus b, and n divides a minus c. By definition of divides, you want equations on this thing, so I need to pull out the definition of divides, declare them before you use them. There exists integers, pick my favorite two guys, x and y, such that now I can write an equation. If n divides a minus b is bigger. So a minus b is equal to nx, and if n divides c minus d is bigger, so c minus d would be equal to ny. Now all that was to work. I had to do two definitions to go from that congruence to finally get my equations. Okay? So, here we go. Here comes the manipulation. Now, I'm going to put over here, now you're never supposed to show me this thing, but I'm doing it for your benefit. Here's my little scrap sheet of paper, so this would never be on my little proof here, but I'm going to put inside this little box, WTS. What do I want to show? I want to show part 2. I want to show that A times C is congruent to B times D mod n. That means, and this is scrap, so I can use little symbolisms on this one because I'm not writing it up yet. Again, this should never be on the thing you turn in. This is on your scrap sheet. I should see the appropriate printed up right, written up work here. So if I want to show that A times C is congruent to B times D mod n, I want to show that n divides, I'll use a little divide symbol there, A times C minus B times D. And to show from the definition of divides, n divides A minus C minus BD, n divides A times C minus B times D, I want to show that A times C minus B times D is equal to n times, here comes, some integer. And I got to tell you who that integer is going to be. At this point, I don't know. This is what I'm after. I'm going to try to get myself an equation on this guy. And how do I end up doing that? Okay? And I'm going to show you this one is a trick. So this is why I want to do this one for you guys. So here comes the trick. So as, I'm going to go ahead now. Remember, all these guys are integers, so I can start out with this guy. So as A times C minus B times D is equal to A times C minus B times D. That's officially the reflexive property. You're equal to yourself. Okay? No one can argue this. X equals X. AC minus BD equals AC minus BD. But here comes the trick right here. Thus, AC minus BD is equal to AC minus BC plus BC minus BD by adding 0. Now, where did I actually add 0 at? This is the trick right here. What is a minus BC plus a BC? That's 0. Now, this is why I wanted to do this one for you guys, because this required a trick. The first one that you have to prove doesn't require a trick. You set it up the exact same way, and then you want to show in the first one, n divides A plus C minus B plus D. So you want an equation A plus C minus B, parentheses B plus D, and you want to see that n factors out of something or other there. So, I added 0. Now, hence, AC minus BD is equal to, now what do I have in common on the first two terms? This is the famous factor by grouping. I have a C in common. I'm going to factor it out. So it'll be A minus B times C plus, what do I have in common on the BC minus BD? I have a B in both of those terms, so I'm going to factor it out, and that's in the front, so that put that out the front. So it'll be B times C minus D. And this was by factor. Factor by grouping is the more appropriate term here. Okay? Alright, now remember what I want to show. I want to show that AC minus BD is equal to N times some integer. I've got to get the N's in there. I don't have the N's in there. So remember these two statements I did from the definition of congruence and the definition of divides. I got some equations now. A minus B equals NX and C minus D equals NY. Therefore, AC minus BD is equal to, well, A minus B, I get to replace with NX times C plus B times C minus D is equal to NY, and that was by substitution. So what do I have in common on this entire side? I have an N in common. This gives us, great linking words here, that AC minus BD is equal to, I'm going to factor out the N, I'm left with XC plus factoring out the N, I got BY. Again by factor. Okay. Notice how I finish this problem. It's going to be a two-stepper because I'm trying to show that, quote, A times C is congruent to B times D mod N, but I got to do two steps to get back to there. Here's the first one. Well, since X, C, B, and Y are integers, then X times C plus B times Y is an integer. And remember, the reason is the sums and products of integers are integers. But there's my sum integer. Therefore, by definition of divides, N divides AC minus BD. Hence, by definition of congruence modulo N, there's lots of different kind of congruence, so you got to tell me which one you're doing. We're doing mod N here. So by definition congruence modulo N, we have AC is congruent, using my symbols here, of BD mod N. And I'm done with my proof. And again, it did require a wee bit of a trick to be able to do this particular proof. Got the adding 0. Minus BC plus BC, that's how you got your terms in there, so you can factor out the C's and the B's and get your N's into the thing so you can factor it out. Definition. Let A and N be integers with N being greater than 0. The congruence class of A mod N, denoted with the pointy bracket A around it, is the set of all integers that are congruent to A modulo N. So in symbolism, this means that this pointy bracket of A is equal to the set of B. That little line means such that. That's how you read the set notation. So this is such that B is an integer and B is congruent to A mod N. This is all the integers that are congruent to A mod N. We denote that by the pointy bracket of A. So, as an example here, we want to look at these guys. So I'm going to look at mod 8. So modulo 8, N is equal to 8 here. Look at the equivalence class 6. Who's in the equivalence class 6? So my little notation here, equivalence class 6 is equal to all the b's such that b is an integer and b is congruent to a, which is 6 mod n is 8. B is congruent to 6 mod 8. By definition of congruence modulo 8, this implies that 8 divides b minus 6. 8 divides b minus 6. Who are the b's going to be equal to? That's what the equivalence class of 6 is going to be. When I plug in a number, I subtract 6, what are the numbers that 8 divides? Because we're in modulo 8. Well, first off, remember you're always in your own equivalence class. So these answers will be, number 1, you're going to have 6 in there. 6 minus 6 is 0. Clearly 8 divides 0. Well, the next one, let's see here, if we do these guys in order, what do I need to subtract off by 6 that 8 can divide? So 8 divides 8, so let's see here, that would be like 14. 14 minus 6 is 8, 8 divides 6. So the next one would be 22. 22 minus 6 is going to be 16, and 8 divides 16. I can go the other way, and let's see here. How about negative 2? Negative 2 minus 6 is negative 8. 8 divides negative 8. And then pretty much I can start running the pattern from this. And so the next one would be negative 10 on this side, dot, dot, dot. On this side, the next one would be 30. The next one would be 38, dot, dot, dot. And I keep on going. Well, how did you get those other ones so quickly? Well, once you got 1, we're doing mod 8. So take your number and keep adding 8 to it, and it'll continue to be divisible by that 8. So this equivalence class 6 is actually the group of integers 6, 14, 22, 30, 38, negative 2, negative 10, dot, dot, dot. And it goes on forever, so it's an infinite size grouping of integers. That's what the equivalence class 6 is going to be. Okay? So, if I go and look at some other ones, let's just do another one of this one just so you can see. Watch this one. What would equivalence class, let's make it 2. What would equivalence class 2 be? If I do equivalence class 2, what we're talking about here is that equivalence class 2 is equal to the set of integers b, so b is an integer, and b is equivalent to 2 mod 8, because we're doing mod 8s on this one. This, by definition, means that 8 divides b minus 2. Okay? So, you're in your own equivalence class because 8 can divide 0, so 2 is going to be in there. And the next one that's going to be in there would be, let's see here, 10, because 10 minus 2 is 8. 8 divides 8. The next one's going to be 18. The one on the low side is going to be negative 6. Negative 6 minus 2 is negative 8. Below that it's going to be negative 14, dot, dot, dot. Above 18 would be 26, and it just keeps on going. And you'll notice that in the equivalence class, that's what equivalence class 2, in mod 8, it looks like it's all these set of integers that have been grouped together. And you notice that they don't have any one of them in common. So, Theorem 2.3 says this, that a, b, n are integers with n being greater than 0. A is congruent to c mod n if and only if the congruence class of A is equal to congruence class of C. Now, to get you guys used to some mathematical notation, if and only if, and mathematically is written IFF, so because mathematicians are inherently lazy, so we're always coming up with short ways of writing up stuff. So A and C are going to be in the same equivalence class. Their equivalence class are equal. Equivalence class of A and equivalence class of C are equal. And what that means up here is equivalence class 6 is the same as equivalence class 14, which is the same as equivalence class 22, which is the same as equivalence class -2. Equivalence class 2 is the same thing as equivalence class 10, equivalence class 18, equivalence class -6, so forth and so on. And because they have nothing in common, two congruence classes modulo n are either going to be identical, they're going to be exactly the same equivalence class, or they're going to be disjoint, which means they have no intersection at all. So what we're doing with this modulo n is we're taking n's and we're subdividing it into particular groups depending on what you mod out by. And you let these numbers, the pointed bracket 6 and pointed bracket 2, represent the number. So, in that setting, let me set you up with this guy here. I want to kind of look at this one, and that is the idea of the, quote, modulo 5. Z mod 5, Z modulo 5. I want to look at each one of these equivalence classes. Equivalence class 0, equivalence class 1, equivalence class 2. So remember, in Z mod 5, it's the set of B such that B is an integer and B is congruent to A mod, we're doing mod 5. And these are A's, 0, 1, 2, 3, and 4. So I'll look at these guys. These are my A's. So what about the equivalence class 0? Well, if you look at the group, equivalence class 0, in other words, what we got here is B such that B is an integer and B is congruent to 0 mod 5. And remember what that means. 5 divides B minus 0. So what are my equivalence classes for this one? Well, 0 would be in there. You're in your own equivalence class. And clearly 5 divides 0. But the next one would be 5. 5 minus 0 is still 5. 5 divided 5. 10, 15, 20, ... -5, -10, ... Those are the integers that make up equivalence class 0 in modulo 5. What about what's going to be equivalence class 1? Well, you're going to be in your own equivalence class, and then basically it's got to be B minus 1 has got to be divisible by 5. So the next one would be 6. 6 minus 1 is divisible by 5. The next one is going to be 11. 11 minus 1 is divisible by 5. The next one is going to be 16, catch your pattern, 21, 26, so forth and so on. It's also go the other direction. It's going to be -4, -9, ... Notice what I'm doing here is really adding or subtracting 5 from each one of these guys. So equivalence class 2 would be the integers 2, add 5 would be 7, 12, 17, 22, 27. It's also going to be, I'm going to subtract 5. It would be -3, -8, so forth and so on. Equivalence class 3 would be 3. 3 minus 3 is 0. You're always in your own equivalence class. I'm going to add 5. That would give me 8. And then 13, 18, 23, 28, going the other way would be -2, -7. And last but not least, equivalence class 4 would be 4, 9, 14, 19, 24, 29, would be -1, -6, so forth and so on. And if you look at all these grouping of numbers all together, every integer has been put in one of these groups, modulo 5. Let me show you. 0, 1, 2, 3, 4, 5, 6. There should have been a 7 there. That's a typo there. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and keep on going and going the other direction. You've got 0, negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, negative 10, and it keeps on going. So every integer has been put into one of these categories. So let's pay attention. This is Z mod 5, but the equivalence classes are 0 through 4. 0, 1, 2, 3, and 4. And we put pointy brackets around to recognize that they are congruence classes. So here's a big deal about this next one here, and that is this. Let n be greater than 1. This is corollary 2.5. Let n be greater than 1. Be an integer and consider the conjugate congruence modulo n. So n is greater than 1 and be an integer and consider congruence modulo n. If a is any integer and r is the remainder when a is divided by n, then here's the big deal. Equivalence class A is equal to the equivalence class of the remainder r. And these are there are exactly n distinct congruence classes modulo n, namely 0, 1, 2, all the way up to n minus 1. And to understand where these equivalence classes are coming from. So if I'm doing Z mod 7, what are the equivalence classes? 0 through 6. Why? Because when you divide by 7, what are the possible remainders? I can get no remainder 1, 2, 3, 4, 5, or 6. I can't get a 7 remainder because 7 divides 7. So it's always 0 through n minus 1. It's the remainders that set up the equivalence class when you do modulo n. And the last is a definition here. The set of all congruence classes modulo n is denoted by Z with a subscript n, Zn, we just call it, and we read it Z mod n. So Z mod 5, Z mod 7, Z mod 9, Z mod 11, Z mod n is how you would read this. And what we're going to be doing in the next couple of sections is looking at a whole new numbering system, because once we got these equivalence classes, we'll be able to add them and multiply them and create basically numbering systems. And these numbering systems become very important stuff. So homework not to turn in. You guys got to know the ones I want you to turn in and attach to the Canvas site here. But I want you to look at problems 1 through 21 odd, but do not turn these guys in. So, and we'll see you guys on the next video when I start section 2.2.